Good day everyone, welcome to the course on next generation sequencing technologies, data analysis and applications. In the last few classes, we have discussed two approaches for genome assembly. The first one was shortest common superstring approach or SCS approach. We have also talked about a greedy version of that, and then in the last class we talked about an approach called overlap layout consensus approach or OLC approach. In this class, we will introduce a new approach which is called the Bruijn Graph based assembly approach, and we will discuss in comparison with the other approaches that we have talked so far. So, this is the agenda for this class. We will be talking about Bruijn Graph based assembly, and here are the keywords for this class. The first one is directed multigraph, the other is Eulerian path. So, just to summarize what we have seen in overlap layout consensus approach. So, there are three steps. The first step is building the overlap graph, then the second step is doing the layout, right, where we remove these inferred edges, right, that can be inferred from other network edges of the network, and then the third approach is the consensus calling, where we determine the sequence of the reference genome. Okay. And we have talked about, right, how repeats can impact this OLC method, but what I would like to encourage you to do is try with different repeat lengths, a number of repeats, and also different read lengths. Okay. And this is where you will start to see is that as you increase read lengths, you start to resolve repeats. Okay. With OLC approach, you will find that as you increase read lengths, you will get to resolve these repeats, and they will not be this unresolvable knots or knot kind of structure in the overlap graph. Okay. And this is where the long read sequencing comes in, right. So, if you remember the first few classes, we talked about short read sequencing and long read sequencing. Okay. So, the problem with assembly, right, that arise from the repeats can be resolved by the long read sequencing, and that is why we prefer to use the long reads when you have to resolve these repeats. Okay. So, I will encourage you to do this, right, with a short reference sequence with different repeat lengths and different read lengths, and you will see with increasing read length you will be able to resolve these repeats better. Okay. So, to discuss the drawbacks, right, so we have mentioned two drawbacks of OLC approach. So, the building overlap graph through pairwise comparison is time consuming. We are doing this billions of these pairwise comparisons, and again each comparison takes time, whether you are applying the dynamic programming or suffix tree based methods. So, that will take a lot of time. Okay. In fact, this is the most time consuming step in the OLC approach, and also the overlap graphs are quite big, right. So, we have billions of reads, each read is present as a node in the graph. So, the structure is quite big, which would have to be stored in the memory. Okay. So, that will consume a lot of RAM. Okay. So, with this in mind, we will now introduce this to Bruijn Graph assembly or DBG assembly, and it is actually very different from all the methods that we have talked so far. Okay. So, first point is that there is no overlap calculation for pairwise comparison of reads. Okay. So, we do not need to do these billions of pairwise comparisons to calculate the overlaps or to identify the number of bases that are overlapping. Okay. So, this is not done in this method. Instead, what we do is the graph that we build here is built by from k-mers from the reads. Okay. So, this is an approach which we will discuss in much more detail. Okay. This is a k-mer based approach where we get this k-mer calculated from the reads. Okay. So, we will illustrate this through some examples. Okay. So, let's now illustrate this approach, right, how we build this. Okay. So, here is a small reference sequence that we will start with. Okay, and we calculate these k-mers, right. So, what are k-mers? So, these are substrings of length k. Okay. So, if you take this reference sequence and if you want to calculate the streamers, right, so you can start from here, right. So, you can see, okay, we start from here and we take these 3 mers, okay, and these are the 3 mers for this sequence. Similarly, you can calculate 4 mers, right. So, we start from this A and we take these 4 bases, right. So, these are the substrings of the reference sequence of certain lengths, okay, and this k can vary, right. Again, depending on the read length, we probably want to have the right k-mer size. Okay. So, this is fine. Now, how we actually go about this assembly or the overlap graph. Okay. So, how do you build this graph in the first place. Okay. So, again coming back to this reference sequence, and let us consider these reads of length 3. So, we say k equals to 3. Okay. And the idea is very similar, you can try different k's. Okay. So, we will illustrate with k equals to 3 and k equals to 4. So, you understand this better. Okay. So, for this k mars, what we do is, in the first step we calculate or split this k mars into 2 k minus 1 mars. Okay. So, if k equals to 3, we have 3 mars, then we need to calculate 2 of these 2 mars. Okay. So, k minus 1 equals to 2. So, we will calculate 2 mars. Okay. So, here is the splitting, that is how it works. So, for this 3 mar k equals to 3, we have the left k minus 1 mar, which is the first 2 bases, right, and then we have the right k minus 1 mar, which is the right which is the 80, right. So, we take the last 2 bases here. Okay. So, it does not matter whether this k equals to 3, k equals to 5, right, we split the k mar into k minus 1 mar. Okay. So, we will illustrate this with k equals to 4. So, you will understand this better. So, once we have done this, we generate this k minus 1 mars from all reads of length k, right. So, what we will do is we take all these reads, okay, and we split them into these k minus 1 mars. You have left k minus 1 mar and the right k minus 1 mar for each of them. Okay. So, this is what we are doing in this step. Okay. So, we start with AAT, we have the left one is AA and the right one is AT. For ETG, the left one is AT, right. So, the first 2 bases, as you can see, this is the left k minus 1 mar and the right one is TG, okay, and so on, right. So, for TGC, this is left one is TG, right one is GC. Okay. So, you understand how we are deriving this k minus 1 mars, and we do this for all the reads that we have in our data. Okay. So, this is what we are doing, right. You can see all the reads we are splitting into left and right k minus 1 mars. Okay. Now, one of the things you might ask, why are you doing this? Okay. What is the point? Why are you splitting these reads into k minus 1 mars? Okay. So, once you have split this, you will notice that this left and right k minus 1 mars, they share an overlap of length k minus 2. Okay. So, for this one, you can see this A base is common between these two, right. So, here k minus 2 equals to 1, right. So, overlap is of length 1. Okay. If k minus 2 is 5, the overlap will be of length 5. Okay. We will see with more examples in this class and the subsequent class, you will see this that the overlap is k minus 2. Okay. So, now we know that overlap is k minus 2, we can now build this graph. Okay. So, how do you build this graph? Because these two k minus 1 mars, they share this overlap, okay, and this for this k minus 1 mar, the suffix overlaps with the prefix of this one. Okay. And with that idea, right, we can build the overlap graph, and this is how it would look like, right. So, this is the left one and this is the right one. The arrow direction would be from the left to the right, right, because of the nature of the overlap, right. So, for the left, the suffix overlaps with the prefix of the right k minus 1. Okay. So, and this overlap is of length k minus 2, in this case it is 1. The edge that we see, if we actually traverse through this edge, this corresponds to this k mar AAT. Okay. Because if we merge this, the overlap is 1 base. So, if we merge this, once we traverse, we can merge these nodes, and this will correspond to the k mar or the read AAT. Okay. So, with this mind, now we can actually apply this for all k mars, okay, and we can generate this directed graph from all reads. Okay. So, what you see here, there is no overlap comparison. What we just do is split the reads into k minus 1 mars, and from that we build the overlap graph. And once we split, we know there is overlap, right, because this left and right k minus 1 mar will share an overlap. We utilize that property to build that overlap graph. Okay. So, there is no pairwise comparison, we just split all these reads into this k minus 1 mars. Okay. So, this is what we have done, right. So, these are the k minus 1 mars for all the reads we have split, and now we will build the graph, okay, and this is the deep brain graph. Okay. So, the first one we have the overlap. So, this is from this k mar or this read, right, we have this connection AA to AT. Now, we move on to the next one, right. So, this one ATG, right. So, AT, when we do this, right, For the first one, it's okay, there are no nodes in the graph. Okay. So, we define these nodes A, AT, and we add this connection. For the second one, right, we have these two k minus 1 merge. So, the first we check whether this node actually exists in the overlap graph already or not, okay, and the answer is yes, right. We see this node already exists here in this overlap graph. So, we just add this connection and we create a node for TG, right. So, we also asked, right, whether this node TG exists in the overlap graph. It does not. So, if it does not exist, then we create a new node and we add the connection, okay. And we do not need to give the overlap, because we know the overlap is same for all of them, right. So, this is k minus 2 for all the edges, right. So, we do not need to add this weight or the edge weight in this overlap graph, because they are same for all the nodes. Okay, so, we move on, right. So, the next step again is the same, right. For TG we ask whether there is a node, and it is there, right, and for GC also we ask whether there is a node. If there is not, so we then create a new node, right, and then add this connection. Okay. So, this is the connection that we have created for this one. In the next step you can probably guess, right. So, for GCT, this one we again ask whether GC is there, GC is here, and then CT is not there in the graph. So, we have to add a new node and add this connection. Okay. So, for up to this point we are done. Now, we are moving to the next graphs, next this k minus 1 merge, and we will see, right, how we can add them. One of the things you might realize, right, these are kind of present in order. So, that is why they are appearing nicely one after another, but in real world they will not appear like this, right. So, when you are considering reads, they will not appear like this. So, they will appear at random, and then based on this you have to define nodes and add connections, etc. But what you will see, this defining this De Bruijn graph construction is not dependent on the order of reads, right. So, whether the reads appear at the beginning or the end, that will not influence the De Bruijn graph. We will see this in a moment, right. So, now I change the order, okay, intentionally. What you see is that now we have this GAA, okay, and we have this GA and then AA. So, here we see AA node, it actually exists, right, in the network, but the GA node does not exist. Okay. So, what we have to do is we have to define this GA node and then add this direction. Okay. So, the direction is always from the left to the right k minus 1 1, right, for the reason that we have already discussed. Okay. So, what we do is we have added this and we can now go into this one, okay, AAT. Okay. So, for AAT, what you see is that we have AA k minus 1 1 and AT k minus 1 1. If you check the overlap graph, what you will see is that both these nodes exist in the graph, right. You have AA and you also have AT. What do you do? Okay. So, we do not need to define any node, we will just add another edge. Okay. So, this is what we are going to do. Okay. So, we will add another edge. Okay. So, you can have multiple edges between nodes. Okay. So, this is kind of getting to the repeat part, right. So, if this part is repeated, you will see these multiple edges. And similarly, we can go to the ATG KMR, right, and then we see, okay, these two nodes again exist. So, we add another edge here and we will have two edges between AT and TG nodes. Okay. Now, moving on, we can now come to this CTG1, right, and what we see is that these nodes actually exist, CT and TG, both these k minus 1 mark actually exist as nodes in the graph. Okay. So, what we need to do is simply add this edge, okay, add this connection, and finally, we have this one TGA, and again we can check whether this TG and GA exist in the graph. Both of them do, right. So, then we add this edge. Okay. So, this actually completes the overlap graph. Okay. So, this is kind of done, right, and one of the things we will do is then we will expand this, right, and say do this for a different KMR, and you will get a better feeling for the whole process. Okay. We will talk about how we actually use these to actually generate the reference sequence a bit later. Okay. So, one of the first things you notice is that in this directed graph we have multi edges, right. So, this is called the directed multi graph because you can have multiple edges between two nodes. Okay. This is unlike the other ones that we have discussed so far. Okay. So, let us take the same reference sequence, but now we define k equals to 4. Okay. So, we will do this for reads of length 4, right, and the step is the same, right. So, we follow the same steps the first thing is we define this k minus 1 merge for all of them. Okay. So, we have to define this k minus 1 merge for all of these reads. Okay. And as you can see, these k minus 1 merge are now of length 3. Okay. And then on top of that, right, you see the overlap is 2 bases, right. So, k minus 2 is 2. So, your overlap between these k minus 1 merge is k minus 2 or 2. Okay. You can see this across all these k minus 1 merge. Okay. Now, we can take this k minus 1 merge, right, and we can now build this directed multigraph following the same process that we just described. Okay. So, we start with this one, let us say, okay, and we have this GGC GCA, right. So, this will be the connection. Okay. Now, we move on to the next one, right, the GCAT. GCA exists in the graph, and we then add this CAT node and add this edge. Remember, traversing this edge will give us the k mark, okay, the read sequence. So, we proceed, right, with this. We have now moved on to this CATG, okay, and again we CAT exists. So, we add this ATG node, and we also add the connection or the edge between these two nodes, okay, and so on. So, we are here now, okay, we are just adding this TGG node, we add the edge. Now, coming here, right, when you come to TGGC, we have these two k minus 1 merge, TGG and GGC. What we see is that both these nodes actually exist in the graph already. So, what we need to do is just add this edge here. You can see this edge here, right. So, from TGG to GGC. So, we continue, right, we have to continue this process until we reach the end, right, until we have covered all the k merges in our data. Okay. So, from GGC to GCA, this actually exists, both these nodes exist, right, and there is a connection already. So, again this will be a multi edge, right. So, we need to add another edge here. So, you will see now also for GCA this one, right. So, for GCAA, GCA exists, okay, and then we define this CAA node and add this connection. Okay. So, now the graph actually becoming interesting, right. So, you have multi edge, you have this again this bifurcation, right, two parts we can go to, okay. And then we come to this point here, okay, where you have this the left k minus 1 mer and the right k minus 1 mer, they are exactly same. The moment they are exactly same, it means this is a self edge. Okay. So, the edge comes out of that node and goes into that node. Okay. So, it is saying, okay, this is present twice, right. So, this k minus 1 mer is present twice. Okay. So, this edge again representing the overlap between these k minus 1 mers. Okay. So, if you kind of interpret this edge, this will be the k mer from the coming out of this edge. Okay. So, now hopefully you understand, right, this concept. We can have multi edge, we can have self edge in this deep brain graph. So, we next move to this AAAT sequence, and we see whether this AAT actually this k minus 1 mers, whether they exist in the graph, right. And we see, okay, AAA k minus 1 mer already exists as a node, and we need to add this AAT, and we add that and add the edge in this graph. And finally, we have moved to this AATG, again we do the check for this k minus 1 merge. So, AAT whether it exists in the graph, it does, and for ATG also it does exist in the graph. So, we add this connection or this edge in this graph. Okay. So, now the directed multigraph is complete because we have utilized all the reads in our data. So, the question is now how we can use this directed multigraph to actually determine the reference sequence, right. So, this is the idea, right. Okay. This is great, we have the directed multigraph. Now, how we can utilize this to generate the reference sequence. Okay. So, the question then we can translate into something else, right. So, if you remember, each edge actually represent a k mer, right. So, can we find a path in that graph that traverses through each edge exactly once? If we can find a path like that, that will actually give us the reference genome sequence, right. So, because each k minus 1 mer is each KMR is represented by the edges, right. So, if we can traverse through each edge exactly once, we have utilized all the reads and we can generate the reference sequence. Okay. So, with that idea, we can look at some of the properties of the graph and we can see whether we can observe any such path in the graph. Okay. So, before we go there, we will define certain terms. The first term is the degree of a node. So, the degree of a node in a graph is defined by the total number of incoming and outgoing edges. So, if you take this small example here, right. So, we have this node GGC and the another node is GCA. So, the degree is 2 for both of them, right. So, for GGC what you see, there are 2 connections going out, but no connections coming in, right. So, it's incoming plus outgoing. So, the degree is 2, and similarly for GCA you have 2 incoming connections, right, but no outgoing edges. So, the degree is again 2. Now, we can also define something called in degree of a node. So, this is the number of incoming edges or number of incoming connections. Also, we can define out degree of a node. Okay. So, these are the number of outgoing edges. So, the degree as we have discussed is just simply in degree plus out degree. Okay. So, now we can define for this very small example the in degrees and out degrees. As you can see, for the node on the left, this one in degree is 0 because there are no incoming edges, and out degree is 2 because there are 2 outgoing edges. And for that node on the right, the in degree is 2 because you have 2 incoming edges, and the out degree is 0 because there are no outgoing edges. Okay. So, now moving on to the full graph, right, the full overlap graph or the directed multi-graph that we constructed, we can now define these in degrees and out degrees for every node in the graph. Okay. So, with that in mind, right, so you can now color code this in degree and out degrees, right. So, we can say red one or the first number is in degree and the second number is out degree. Okay. So, for this one, as you can see, you have just one incoming edge, right. So, this one here. So, the in degree is 1 and you have 2 outgoing edges. So, out degree is 2. You can actually look for incoming edges and outgoing edges for each node in the graph. So, for this one GCA, it is 2 2 because we have 2 incoming edges and 2 outgoing edges. So, similarly, you can define this for every node in the graph, right. For these ones, right, this is simple, they have just one incoming edge and one outgoing edge. Here you can probably see, right, you have 2 incoming edges and 2 outgoing edges, right. So, the self edge, so for the self edge you have one incoming edge and one outgoing edge, right. So, that is why it is 2, okay, in addition to the one that is coming in and going out from this node AAA. Okay. And finally, for this one here you can see 2 incoming connections. Okay. So, you have these 2 connections, right, one from here, one other from here. So, in degree is 2 and out degree is 1. Okay. So, we have now defined the in degrees and out degrees for each of these nodes. Okay. So, why is it important? What are we going to do with these in degrees and out degrees? So, it turns out is that we can define certain things that will tell us whether there is a path that we just want. Okay. So, for that what we do is with these in degrees and out degrees, if a node has equal value of in degree and out degree, that node is called balanced. Okay. So, we will call a node balanced if in degree is out degree. We have seen certain nodes in our graph, right. So, that where the in degree is equal to the out degree. In addition, a node is called semi balanced if the absolute difference between in degree and out degree is 1. Okay. So, in degree could be higher than out degree or out degree could be higher than in degree, that does not matter as long as the absolute difference in the value is equal to 1. Okay. So, they can differ at most by value of 1. Okay. So, with this in mind, now we can check our graph and see whether we have balanced and semi balanced nodes. Why are these important? Why are we interested in this balanced and semi balanced node? So, we will actually introduce this concept of something called Eulerian path. Okay. So, there is a path, right, in a graph, if that path exists, right, so this will be a Eulerian path. So, this is a path that visits each edge of a graph exactly once. Okay. This is something what we wanted, right. This is the question we framed a few minutes ago, right. So, this is the path we want. Okay. This is a Eulerian path that will visit each edge of a graph exactly once. Okay. and there is a condition that has been seen, okay, that a graph is Eulerian, meaning there would be an Eulerian path if and only if it has maximum 2 semi-balanced nodes and the rest of the nodes are balanced. Okay. So, we find a directed connected graph where you have at most 2 semi-balanced nodes, okay, and rest of the nodes are balanced. So, we have defined these balanced and semi-balanced nodes just now. Okay. So, following that idea, right, if you have at most 2 semi-balanced nodes, we can say, okay, there is a Eulerian path in that graph. So, this actually helps us beforehand, right, before we try to find a path, Eulerian path, beforehand we know whether such a path exists or not, right, whether we should try to find that path at all. Okay. So, with this in mind, now let us actually move to our graph, right, and see whether we can find an Eulerian path, right, whether this exists, whether this condition is satisfied. So, which will tell us whether such a path will exist, and then try to find the Eulerian path, right, because if we can find the Eulerian path, we will get to derive the reference genome sequence. Okay. So, again back to this graph, right, we have this in degrees and out degrees. What you notice is that most of these nodes show equal in degree and out degree values, right. So, if you consider this one, right, these are all showing same in degree and out degree value, right. So, these are balanced nodes, okay, as we have just defined. But for these ones, right, this one and this two, right. So, these two nodes, they are not balanced, but as you can see they are semi balanced, right. The difference between in degree and out degree is just 1, okay. So, these two are semi balanced nodes, okay. So, if you have these semi balanced nodes and they are at most 2 in the graph, this means that there is a Eulerian path in this graph, okay. If you remember the condition, there could be at most 2 semi balanced and rest of the nodes should be balanced. So, this condition is satisfied for this graph. So, which means there is an Eulerian path, okay. So, now that we know there is an Eulerian path, we can actually search for it and traverse through that path, and that will give us the reference genome sequence. Okay. So, let us find the Eulerian path in that graph. Okay. So, usually we start from a semi balanced node where out degree is greater than in degree, because that is where we will have an extra out degree or an extra outgoing edge, right. So, in this case it is this node here, this is semi balanced, and this out degree is greater than in degree, right. So, we start with this here, and as we traverse this edge, we are getting the reference sequence. Remember, right, each edge is a KMR, right. So, that is the sequence. Okay. Now, we have traversed through this, and now we have two options, right. We can take this direction or we can go in this direction. Okay. As you will probably see, right, this will if we come in this direction, we might not actually get the Eulerian path, but we can try, right, again. But let us now traverse through one direction and see whether we get the reference sequence or not. Okay. So, here is this one, right. So, we are going to this CAT. So, we are also adding this to the reference sequence, and then we go to this ATG node, right, and we are adding this to the reference sequence here again, right, keeping in mind the overlap between these two adjacent nodes or the edge that we are traversing. Okay. And as we traverse through these edges, we actually build up the reference sequence. Okay. So, I am highlighting this traversal through these red arrows, as you can see, and we continue this process, right, and we are traversing every edge exactly once, right. This is very important here. Okay. We need to remember this. Okay. And here we traverse through the self edge, okay, and then finally we have traversed through all the edges. Okay. And this is the reference sequence that we have got after this edge. Okay. And this actually turns out to be the correct reference sequence. But one thing I will tell you is that there might be multiple Eulerian paths in a graph, and they might not always give you the right reference sequence. Okay. So, there are options again to find these Eulerian paths and to see which one would be the best reference sequence. Okay. So, here are the references for this class. So, we have discussed the DBG method, we have introduced how it works, right. So, we see the reads of length k are first split into left and right k minus 1 mers, and these left and right k minus 1 mers have overlap of length k minus 2, and we also generated this directed multigraph from these k minus 1 mers, which are then used, right, to actually determine whether there is an Eulerian path in that graph, and if that path exists, we traverse on that Eulerian path, which gives us the reference sequence. Thank you very much.